length of conductors significantly impacts voltage drop and the required size of the equipment grounding conductor, often abbreviated as EGC. Voltage drop in conductors is calculated by multiplying 2 times the length of conductors, the load current, and the resistance of the conductors. The resistance depends on the size and material. As an example, for 250 kc mil copper conductors, the resistance is 0.50 ohms per 1000 feet. Consider a scenario with a 500-foot run. The voltage drop equals 2 times 500 feet times 250 amps times 0.50 ohms per 1000 feet, resulting in 12.5 volts. This voltage drop is significant because it reduces the voltage available at the load. To compensate, the equipment grounding conductor must be sized adequately to handle fault currents. The minimum equipment grounding conductor size based on the proportional increase is calculated by multiplying the phase conductor size by the load current, then dividing by the rated ampacity of the phase conductor. If you have 350 kc mil phase conductors with a rated ampacity of 370 amps and a 250 amp load, the calculation would be 350 kc mil times 250 amps divided by 370 amps, resulting in roughly 236 kc mil. However, the equipment grounding conductor must be sized to carry the same amount of current as the phase conductors under fault conditions. The equipment grounding conductor should be at least 250 kc mil in this case. Now let's delve into some key aspects related to equipment grounding conductors and voltage drop. Firstly, the National Electrical Code, or NEC, provides tables for equipment grounding conductor sizing based on the overcurrent protective device size. These tables are essential for ensuring safety and compliance. Secondly, voltage drop calculations are crucial for determining the appropriate conductor size to maintain adequate voltage at the load. The NEC recommends limiting voltage drop to 3% for feeders and 5% overall. Thirdly, the proportional increase method is used when the equipment grounding conductor needs to be increased in size due to an increase in the phase conductor size for voltage drop. This ensures the equipment grounding conductor can handle the increased fault current. Fourthly, conductor material plays a significant role. Copper and aluminum have different resistance values affecting voltage drop and equipment grounding conductor sizing. Copper is generally preferred due to its low resistance. Fifthly, installation methods also influence ampacity. Conductors installed in conduit have different ampacity ratings compared to those installed in free air. This must be considered when selecting the appropriate conductor size and equipment grounding conductor size. Sixthly, the length of the conductor run is critical. Longer runs result in higher voltage drop, necessitating larger conductors and equipment grounding conductors. Seventhly, temperature correction factors must be applied to ampacity ratings based on the ambient temperature and the conductor's insulation rating. This ensures that conductors don't overheat. Eighthly, parallel conductors require careful consideration. When using parallel conductors, the equipment grounding conductor must be sized based on the total ampacity of all parallel conductors. Ninthly, grounding electrode conductors connect the equipment grounding system to the earth. These conductors must be sized according to the NEC based on the size of the service entrance conductors. Tenthly, bonding jumpers are used to connect different metallic parts of the electrical system to ensure a low impedance path for fault current. These jumpers must be properly sized and installed. 11thly, ground fault circuit interrupters, or GFCIs, protect against ground faults by detecting small imbalances in current. They are commonly used in wet locations and areas where electrical hazards are high. 12thly, arc fault circuit interrupters, or RFCIs, protect against arc faults which can cause fires. They are required in many residential circuits. 13thly, surge protective devices, or SPDs, protect against voltage surges caused by lightning or other electrical events. They divert excess voltage to ground. 14thly, proper grounding and bonding are essential for electrical safety. They provide a low impedance path for fault current, reducing the risk of electric shock and fire. 15thly, regular inspections and maintenance of the grounding system are crucial. This includes checking connections, testing ground resistance, and ensuring all components are in good condition. 16thly, understanding the NEC requirements for grounding and bonding is essential for all electrical professionals. The NEC provides detailed guidelines for safe and effective grounding practices. 17thly, proper documentation of the grounding system is important. This includes recording conductor sizes, grounding electrode locations, and test results. 18thly, continuous improvement in grounding practices is necessary. Staying up to date with the latest technologies and techniques can enhance electrical safety and reliability. 19thly, training and education are vital for electrical workers. Proper training ensures they understand the principles of grounding and can apply them effectively. 20thly, collaboration between engineers, contractors, and inspectors is essential. This ensures the grounding system is properly designed, installed, and inspected. Now let's talk about specific NEC tables. NEC Table 250.122 provides the minimum size of equipment grounding conductors for alternating current systems. This table is based on the size of the overcurrent protective device protecting the circuit. For example, if the overcurrent protective device is rated at 300 amps, Table 250.122 requires a minimum of number 4 AWG copper or number 2 AWG aluminum for the equipment grounding conductor. The table also includes notes that provide additional guidance on sizing the equipment grounding conductor in certain situations, such as when parallel conductors are used or when the ungrounded conductors are increased in size for voltage drop. When ungrounded conductors are increased in size for voltage drop, the equipment grounding conductor must be proportionally increased in size as well, as discussed previously. This ensures the equipment grounding conductor can adequately handle any fault current that may occur. It is important to note that Table 250.122 provides the minimum size for the equipment grounding conductor. In some cases, a larger equipment grounding conductor may be required to meet other requirements such as those related to impedance or voltage drop. For example, if the circuit has a long run, the impedance of the equipment grounding conductor may need to be reduced to ensure that the overcurrent protective device will operate quickly in the event of a ground fault. In this case, a larger equipment grounding conductor may be required. Voltage drop is another important consideration when sizing conductors and equipment grounding conductors. Voltage drop occurs when the voltage at the load is less than the voltage at the source. This can be caused by the resistance of the conductors and the current flowing through them. Excessive voltage drop can cause equipment to malfunction or not operate at all. To minimize voltage drop, conductors must be sized large enough to carry the load current without excessive voltage drop. The NEC recommends that the voltage drop on feeder circuits not exceed 3% and that the total voltage drop on both feeder and branch circuits not exceed 5%. To calculate voltage drop, use the following formula: voltage drop equals 2 times L times I times R divided by 1000, where L is the length of the conductor in feet, I is the current in amps, and R is the resistance of the conductor in ohms per 1000 feet. The resistance of conductors can be found in NEC Chapter 9, Table 8. This table provides the resistance values for various sizes and types of conductors. Once the voltage drop has been calculated, it can be compared to the recommended limits to determine if the conductors are adequately sized. If the voltage drop exceeds the recommended limits, the conductors must be increased in size. The equipment grounding conductor must also be increased in size proportionally if the ungrounded conductors are increased in size for voltage drop. In addition to voltage drop, impedance is another important consideration when sizing equipment grounding conductors. Impedance is the opposition to the flow of alternating current. It is similar to resistance, but it also takes into account the effects of inductance and capacitance. High impedance in the equipment grounding conductor can limit the flow of fault current, which can slow down the operation of the overcurrent protective device and increase the risk of electric shock. To minimize impedance, the equipment grounding conductor should be short, straight, and have a low resistance. The connections to the equipment grounding conductor should also be clean and tight. The NEC provides guidance on impedance requirements in Section 250.4. This section requires that the impedance of the equipment, ground, and conductor be low enough to allow the overcurrent protective device to operate quickly in the event of a ground fault. To verify that the impedance is low enough, an impedance test can be performed. This test measures the impedance of the equipment, ground, and conductor and compares it to the maximum allowable impedance specified in the NEC. If the impedance exceeds the maximum allowable value, the equipment, ground, and conductor must be improved. This can be done by shortening the length of the conductor, using a larger conductor, or improving the connections. In summary, sizing equipment, grounding conductors and conductors requires careful consideration of several factors, including the size of the overcurrent protective device, voltage drop, and impedance. The NEC provides detailed guidance on these requirements, and it is important to follow these guidelines to ensure a safe and reliable electrical system. Remember to always consult with a qualified electrical professional for specific applications.